Hi, this video will cover section 2.2, polynomial functions of higher degree. We'll be using transformations that we previously learned in section 1.6 to sketch graphs of polynomial functions. We're going to introduce the leading coefficient test and use it to determine the end behavior of graphs of polynomial functions, such as the parabola. The end behavior will be like both sides go up or both sides go down. The third one is find and use the real zeros of polynomial functions as sketching aids, and finally use the intermediate value theorem to help locate real zeros of polynomial functions. So as I have mentioned previously, graphs of polynomial functions, they are continuous, and for example the linear function is a polynomial. That one is a line. But then after that, we start seeing these little curves, or we call them critical points, like the vertex of a parabola. And also, polynomial graphs are continuous. And as you can see, there are no breaks or gaps in between, like for example, a piecewise function, or the step integer function, or a rational function. These ones are continuous, which essentially means that the graph of the polynomial has no breaks, no holes, no open circles, or gaps. So here we have, on the left, we have graphs that are not polynomials. And this one, for example, is what I was mentioning about piecewise functions. It is piecewise. And also, it is not continuous. You can see that gap here. So there's a break. And then the graph on the right, it is a polynomial. It is smooth and it has rounded turns. So for example, the absolute value, the one that is like a V shape, that is definitely not a polynomial graph. It has a sharp turn. So this one is not included, definitely. And this one is. No gaps and just smooth turns. Now, as you can see, this one has more turns than a parabola, a quadratic function of degree 2. And that is determined by the degree of the polynomial, but we'll study all of that. Oh, and just what I was saying, the absolute value is definitely not a polynomial graph because polynomials cannot have a sharp turn. So the absolute value, as you can see here, we have graphed that before. The turn is at the origin at the point 0, 0, and definitely is a sharp turn. So of course it cannot be the graph of a polynomial. Also, polynomials, we will come to the formal definition, but they are functions where the independent variable is raised to a certain exponent, such as here x to the power n, where n is an integer that is greater than 0. Now, when we define a polynomial, we could include n equal to 0 because we were considering constant functions to be polynomials of degree 0. Now, on this slide, we are talking about the polynomial functions that have the simplest graphs of this monomial form. And these ones, they actually do have a name. They're called the power functions. So for example, if we have here we have x to the second power here. Actually, let's go ahead and grab x to the first power, which will just be a line. And it also passes through the origin. and through those points 1, 1, and negative 1, negative 1. So you could see here that the polynomials that we have here have a degree that is odd. So such as 1, that's an odd number, 3 is odd, 5 is odd. So for those 3 polynomials, we could say that n is odd, and the graph crosses the axis at the x-intercept. Just like any x-intercept, it will be through the x-axis. Now, sometimes the intercepts, for an intercept, the graph may cut across or just simply touch it and turn back around, as we can see here with the even degree. If the degree n, that you can see here, the exponent, is even, then the graph will touch the x-axis and then it will turn around, as you can see here with the vertex of the parabola, the one of degree 2. And then here we have the polynomial of degree 4, the quartic function, and that also touches and it turns around. Now, as you can see, it looks flatter, the space that it touched, the graph of x to the power 4, it looks flatter at the origin, and well, that is because it's doing that touching and turning more than once, but we will go over that. So one thing I want you to notice is how when the degree is even, the behavior of the graph, the end behavior, it shows that both sides go upward. So it has the same end behavior, where the ones that are of odd degree, it has one side falling and one side rising. And we could see that with all of these polynomials of odd degree. So they have opposite. And so with the leading coefficient test, we're going to learn how to determine if they have, if both sides go up or both sides go down, or in the case of the odd polynomial, with which side will be going up and which side will be going down. So we have the graph here of negative x to the power 5. And as you can see here, it has the opposite end behavior that I was talking about. And also it does have the reflected end behavior of the same polynomial if it had the degree, the same degree, but with a positive coefficient. So let me remove the one in red. So you could see this is positive x to the 5th. So we could see how the graph is just like the ones on the slide that we were looking at. Oops, not there. Right here, the ones with odd degree. And so the one that I graphed in green on Desmos is the x to the 5th. So it matches this one. They all have a positive leading coefficient because even though you cannot see it, you know it's a positive one in front of it, right? So that is the same end behavior of this one, x to the positive x to the 5th, right? So if I put a negative in front of it, then it looks like that, like a reflection across the y-axis. So you could see that here it will be rising on the left, falling on the right. And that is because the leading coefficient switched to a negative 1. Now let's look at the one with x plus 1 to the power 4. So that is similar to the one that we observe of x to the power 4th. However, here we have that plus 1, which is shifting the, it's not called a vertex because this is of degree 4. but the x-intercept, let's call it that, is switching the x-intercept from 0, 0 to -1, comma 0. Remember, horizontal shifts are counterintuitive, so if you see a +1, it actually moved to the left. Okay, so let's just trace some here quickly. And we're just gonna do a very rough sketch. So that one was, it looked like that. And then the other one, it was here at -1. And then it touched the x-axis there. It looked a little flat here. Not as, not like a vertex of a parabola. Okay, but we see the same, even degree, odd degree. So we see opposite in behavior for odd degree and same behavior for even degree. Okay, and I don't want you to confuse this with even. Oops. There's a thing called even function. And there's a thing called even polynomial. These are not the same because even function applies to any function, not only polynomials, and that's when we substitute -x. And if we get the exact same function, it's an even function. But when we substitute -x and we get not the same, but the complete opposite of the original function, that's what makes an odd function. We study this in chapter 1, and I just want to tell you that this is actually very useful when you get to calculus, or if you plan to take any math higher than that, than calculus. It's something that it always comes back. So even polynomial is one thing, even functions another thing. Okay, so right here we have a summary of what the leading coefficient test will be. And as you can see, we have the definition for a polynomial written here. And this was in our previous section, but however, we were only using it for x to the second power because the higher degree was 2 for a quadratic. Now we're going to generalize this a little further, and we will say that n could be any degree. So if that n happens to be odd, like the numbers that we already seen, like the, for example, n is a 1, a 3, a 5, and so on, those are the odd numbers, then we have that opposite n behavior that you could see here. One side goes up, one side goes down. And so here's the key. If the leading coefficient is positive, meaning greater than 0, and remember, this is the leading coefficient, the coefficient of the term with the highest degree, which will be determined by n. Okay, so if that is true, then the graph will fall to the left, as you could see here. And it will rise to the right, as you could see here. All right. Now, what happens if the leading coefficient is negative, meaning less than 0? Then the graph will rise to the left and it will fall to the right. Now, I don't want you to get confused with the terminology that we used about increasing and decreasing, because here we're only talking about the end behavior, only about like the tails of the function. When we talk about increasing and decreasing, we use those terms to describe the whole function behavior, like everything that happens in between. And we do state the specific intervals of x values where those changes occur. And when we talk about and behavior, we're just concerned about what's happening on the left and the right side of the graph. Um, and that is determined with the degree of the polynomial. And second, with the leading coefficient. So remember, the degree is n, and the leading coefficient is a sub n. On the next slide, we could observe the other case when the degree, the n, will be even. And if there's one thing that I really want you to have on your notes is these two boxes, because this is very, very important. And on your homework, quizzes, and exams, you will see something that will be in reference to this. And so it will be very useful if you have it handy on your notes. Like you could even put it in a note card. I forgot to tell you guys that if you prefer to do your notes on note cards, you're welcome to do that. They don't have to be on like full sheets of paper. Also, as I grade the notes, I notice that all of you do them on paper. And you have the opportunity, especially if you have a touch screen or an iPad, you or a tablet, you have the opportunity to write your notes and keep them in an electronic way, such as OneNote. That's the program that I use. This one right here. All you have to do to find it, you all have it. If you have Microsoft, you have OneNote. So all you gotta do is type on your keyboard OneNote, and you see it shows up. Oops, maybe I have to fix this a little bit. It shows right here, OneNote. You click on it and you'll have one. You might have to sign in. I'm signed in with my personal email, I think, but you all as students of EPCC, you also have access to it. I know some professors use it for their classes, so it would be a good idea if you start um, getting familiar with it. It's very, very convenient. Okay, so going back to our lecture. Sorry, I get off topic. So when the degree is even, okay, that means that we have degree as one, I'm sorry, oh my God, no. 2, 4, 6, and so on, right? So in this case, we will have, of course, two cases. One will be when the leading coefficient is positive, meaning greater than 0. So both sides will be going upward. But the vocabulary they use for this specific section is the graph rises to the left, so it goes up to the left, and it rises to the right, goes up, like the sun rises every morning. Now, when the degree is still even, but the leading coefficient in this case is negative, meaning less than 0, then we know that the graph falls. It falls to the left and to the right. So you could see it here. That's what we call downward, both sides with the parabola. That's what we were saying, right? So this is another way to say that. Falls to the left, falls to the right. So both sides go down, both sides go up. The ends of the graph, okay? Now, the dashed portions of the graph that you see here, they're indicating that the test determines only the right hand and the left hand behavior. So only the tails. Okay? We don't know what's going on in between. That's what the dash lines indicate. They could be like 4 turns, 3 turns, or whatever. Okay, so now with example 2, we're going to describe the right hand and left hand behavior of the graph of the function. Remember, we call this the and behavior. Okay, so first polynomial, we see that the degree, which is denoted by the letter n, is a 3. We know obviously that's an odd number. And so we know we're going to have opposite in behavior, right? So this one is kind of like a linear function because a linear is power degree 1. So it's 1 on each side, right? Now, how is that going to work? Well, we need to know what a sub n is. A sub n is the leading coefficient. You can see a negative here in front of the x cubed. So we know the leading coefficient is negative 1, like that. So because of that, we are going to have the case similar to a linear function with a negative slope. Remember we talked about those, how they lean to the left, like that. And so that is actually the behavior that we want to keep, like that, but except we don't want a line. So this graph is of degree 3. So and I'm just going to do a very rough sketch, but remember, you could always use your calculator, use Desmos. There's nothing wrong with using technology. Now, I might warn you that you might encounter a professor who might not allow you to use a calculator. So yes, that does happen. Okay, so we have our polynomial there. It didn't say to draw it, I just wanted to do it. So to describe the end behavior, it will be that it rises. Let me see exactly the words they use. Rises to the left. And I mean, this is like a very bad third degree polynomial because of the turns. Oh, there we go. Rises to the left, and it also falls. Is it to the right or from the right? To the right. It falls to the right. In other words, it's going up on the left, so we use the word rises, and it goes down on the right, so we use the word falls. Okay, next polynomial. So we have degree, biggest exponent is 4. Leading coefficient is the coefficient of the x to the 4th. We don't see a number, however, it's positive, so we assume it's a positive 1. And we see it's even degree, and the leading coefficient is positive. So this reminds me of the parabola. That's like the easiest thing, right? If the leading coefficient is positive, it's smiling. Both sides go up. However, this is a 4th degree, so perhaps we might see some little turning points. That's what we call them. We'll discuss them in a minute. And it looks like that. And these are very rough sketches, okay? If you go on Desmos and graph them, that will give you a better idea. And then, you could always zoom in, zoom out, and then describe them. And yes, you're allowed to use technology. But it's important to know how to do it by hand as well, or understand why. And that's why I like for you guys to take notes. Also, it is proven that when you write something by hand, it helps you take that new knowledge that is in your short-term memory and it allows you to put that information in your long-term memory. Okay, so here we're going to say it rises to the right and it also rises to the left. Okay, let's do one more. So here degree is 5. We know it's an odd number, so it's odd degree. And we see the leading coefficient is, what is it? Positive 1, because we don't see 1 there. So it's positive 1. So here we're going to have odd degree. So we're going to have opposite in behavior. However, because the leading coefficient is positive, remember those lines with positive slope, they were leaning to the right. So I want to mimic this behavior here. So what I'm going to do, and because it's of degree 5, perhaps I might have more turns in between. 1, 2, there we go. Let me see if this is possible. 1, 2, 3. Yeah, I mean, it's possible. Most polynomials of degree 5, they have 4 turns. They could have less, but let me just do something better. Yeah, so 1, 2, 3, 4. No, that wouldn't work. Okay, let's just do the dots so we don't know what happened here. That's better. Because we're only concerned about what's happening at the end. Remember that. So we're gonna say that it rises to the right and it also falls to the left. Okay, and that's it for the leading coefficient test. It's pretty easy. These are easy questions on the homework, and so I hope that you guys really get to it. Okay, we have here, what is this? Oh gosh, this is the actual solution. Oh, well, great. Let's look at the actual graphs. Let me see if it's the same for all. Yes, it is. So let's just go over that quickly. We already found our own solution. So these are the real graphs, not the rough sketches that I was drawing over here. But let's see if we were right. And yes, I think we are. So rises to the left, falls to the right. Pretty good, right? We had that degree is odd and leading coefficient is negative. Next one was degree is even, leading coefficient is positive. So the graph rises both sides to the left and to the right. Then here we had degree was odd, leading coefficient is positive. So the graph falls to the left and it rises to the right. So we did great. All right. Now let's talk about real zeros. When we say real, we mean they belong to the set of real numbers. That includes positives, negatives, fractions, rationals, irrationals, decimals. They're all real. And when we say zeros, I remember we went over briefly, but I will repeat it. The word zeros, it means I'm going to write it up here. The x values for which y is equal to 0. Ooh. Oh my God. Okay. In other words, when x is certain number, let's call it c for a constant, the y value is 0. Or in other words, you have them as a point and it will be a constant and then 0 for the y. So if they are real zeros, we also refer to them as x-intercepts because they are on the x-axis. Some are very easy to find, some are not so easy to find, but in the following sections, we're going to go over some techniques on how to find them. So let's see. We also have another word for them. We call them solutions to the polynomial. And it's because if we substitute f equals c and we substitute the y value with a 0, that c value will be the solution. We also call them roots of the equation. And in fact, for solutions, those we list them this way. It could be something like that. Just C and A are just numbers, different numbers. Roots, I guess the same. And then when we call them in x-intercepts, they must be real numbers. So it will be something like A, 0, C, 0. And when we say that they are the x values for which y is equal to 0, we could think of this. They're the solution to this equation. Okay, so depending on the degree of your polynomial, that's how many zeros you will have. So if the degree of the polynomial function is n, then you're going to have at most n real zeros. Now, we use the word at most because we could have up to n, but we could have less. So the number of zeros could be less than or equal to n. That's what the word at most represents. The most number of zeros is n. So the other possible number of zeros needs to be less than that. It cannot go past. Okay, number 2. The graph of f has at most n minus 1 turning points. So turning points, we have seen them, those little curves. I told you they're called, in calculus, we call them critical points because they're very important. And here we're just going to call them turning points. And as you notice, it's always one less than the degree. And we could call them relative maxima. We could call it relative minima. And we could call them absolute minimum or absolute maximum if it was a closed interval function, like not with a domain that goes to negative infinity to positive infinity, or perhaps the parabola. That one does have the absolute minimum or absolute maximum because it only has one turning point. But with the rest of polynomials, we use the word relative because it is relative to what piece of the graph we're analyzing. And we will see that with the examples. And to find those are the points where the graph changes from increasing to decreasing or vice versa. So finding the zeros of polynomial functions is one of the most important problems in algebra. In pre-cal, perhaps you might not be able to, in pre-cal 1 maybe, to see a lot of importance, but as you move on throughout the minimester or semester, or when you take pre-cal 2, you learn more about why they're important. But if you do take calculus, all of this just makes so much sense, and you start learning how important they are and what kind of problems you could solve in not just algebra, but in many, many subjects, including engineering, including degrees like fields like biology, chemistry. Math is actually used in them too. I don't want to scare you if you hate math and that's what you're going to study, but they are very important and they are helpful and they are very applicable. Okay, so here, a little summary. This will be a good thing to write on your notes. So if you're not so sure what to write on your notes, I mean, I would prefer you write everything, right? But that it's time consuming. I personally, as a student, when I'm watching a lecture video, I pause it and then I write everything, even though we have the PowerPoints. And then I might have to rewatch the videos, but that's just how graduate school is. So, very important. Everything that you see in a little table, that's something that perhaps you want to have on your notes. And a little bit of examples. And perhaps you don't want to write all of this stuff here, but this stuff here, yes, for sure. Okay? So let's see. Real zeros of polynomial functions. When f is a polynomial function and a is a real number, the following statements are equivalent. So we could go from one to the other, and we can go from 1 to 4, 4 to 3, 2 to 1, and all the way, like in any direction. So if we call a that number, remember a is a number, if we say a is a zero of function f, then we could also say x equals a is a solution. When you're entering your answers on WebAssign, make sure that like they either they have x equals already outside, they just want you to enter the number, or they might want you to enter it with the x equals and then the number. Or they might just have the answer box and for you to enter the number. So I know they're tricky. So zero solutions. And then this is actually very important. If we take x equals a and we say that's a solution. So if we take this positive a, remember a is a number, to the left, it's going to be subtracting, right? Or similarly to saying minus a minus a. So then we get x is equal, I'm sorry, well, we start with x equals a, so now it's going to be x minus a is equal to 0. You see? And so then we could refer to this x minus a as a factor for the polynomial. Now, also, we have one more. If a is a real number, this is only true for real numbers, not for imaginary, which we will see in this chapter, then we could refer to it as an x-intercept. So the x-intercept will be at the point, remember, a, comma, and by default, the y value must be 0. So in this chapter, we're going to study several ways to find the real zeros and imaginary zeros later on. So, sorry about that. Tommy, stop. Okay. So just like we were to find a real, an x-intercept, we always say, or we used to say, but we will still say it, and you will say it forever, you let y equal 0. Now, we know that for function notation purposes, we use f of x, so it's the same thing. You let f of x equal 0, or you set f of x equal to 0, meaning that part of the equation will be, actually, let's move it a little more. It will be equal to 0. Then I'm going to copy the rest. Negative 2x to the fourth plus 2x squared. Okay, then from here, once it is equal to 0, we could factor. And so what I want to do here is factor the greatest common factor, which is going to be x squared for the variable, but we could also factor a 2. Now, we could factor a 2 or a negative 2. Let's try with a negative 2. X, we always take the smallest exponent if we want to factor a variable. So if we factor negative 2x squared from here, from negative 2x to the fourth, it's like we are dividing the two terms, and so the exponents get subtracted. And it's like we have something like this. Negative 2x to the fourth divided by negative 2x to the second power is going to be x to the second power. Then we're going to factor the same from here. So that's going to be from positive 2x squared divided by negative 2x squared. That's what we're factoring out. So we're going to get a negative 1. Oops, so let's change this plus with a minus 1. Okay, now from here, this part happens to be a difference of squares, because you could take the square root of x squared, you get x, and you can take the square root of 1 and you get 1. So we call those difference of squares. You could Google it if you don't remember how to factor those. But we factor them as the product of two binomials, where we take the square root of x squared, xx. We take the square root of 1 is 1 and 1, or more specifically, plus 1 and negative 1. So that's how we factor the difference of squares. Now, once you get to this point where you have your factors listed equaling 0, you take each factor at a time and equal it to 0. And then what you're going to do is you're going to solve for each factor at once. We call this the zero factor property. So here, if I solve for x, it will be x squared x squared is equal to 0 divided by negative 2. So x squared is equal, I have to keep moving this, x squared is equal to 0. So if we take the square root of 0, we will get 0. So that first x-intercept, you could see it here at the point 0, 0. Then for the next one, we are going to solve for x, so we're going to subtract 1 on both sides, or simply move the plus 1 across the equal sign so it turns into a negative 1. And that will be our second. And it will be here at negative 1, comma 0. And then the last one we have here will be x is equal to, we take this negative 1 across, inverse operation is addition, so it turns into a positive 1 or just a 1. We don't need the positive. So right there, our third solution is giving us our third x-intercept, which will be right there at 1, comma 0. The 0, 0, it happens to be Also a y-intercept because it's at the origin, so that is serving both purposes. But I want you to notice how for the x equals -1 and the x equals 1, the graph, it, how could we call this? It cut through the x-axis, or let's say it went through the x-axis, or let's say it crossed x-axis. And so did this one, a positive one. Now, if you look at what's happening at the origin, at x equals 0, that one did not cross the x-axis. In fact, it touched it and then it turned around. And so this one, touch and turn around, or some people refer to it as it bounced. It turned around. And so I want to tell you why. That is because for the zeros that just cross the x-axis, the degree of the factor, remember we had our 3 factors listed here, it was a degree 1, degree 1, degree 1, but the degree of this one is a 2. And that 2 is making this behavior happen, the touching and turning around, because it is repeating an even number of times. Okay, so to summarize what we did in example 3, when we have repeated zeros, and those come from the factors that have a power that is greater than 1, such as the factor that we had that was -2 x squared. And so we had the repeated zero of x. How many times? Well, that depends on the exponent here. So because we had that x equals 0, we could say it twice. That's what caused our graph to bounce. So how do we know? If we also refer to this as the multiplicity of the factors or the zeros. And so if that multiplicity is an odd number, then the graph is just going to cross the x-axis. If k is odd, and we're not talking about the degree of the polynomial, we're talking about the degree of the factors of your polynomial. So the graph will cross the x-axis, just like we saw it here, right? We had the polynomial, the factor 1 time. 1 is also an odd number. So if that factor had been a 3, because 3 is also odd, the same behavior would have occurred, just crossing the x-axis, because the multiplicity is odd. If k was 1, 3, and so on, odd numbers. Now what happens with k is even? Well, just like we saw with our example, we found the 0, and then the graph will touch the x-axis, and then it turns around. It says here does not cross, so I like to say turns around. I don't know if you guys have ever heard that song. It's super old. I wasn't even born when it came out, but it's famous. The turn around, Every now and then I get a little bit. Yeah, that one. So I had students who used to always sing that. When I ask what's gonna happen at that zero, and they will sing that song. It will turn around. This we're in high school. You're older than that. Okay, next. Well, let me give you some like just quick examples. So let's say that we had a polynomial and we already had it factored, and so we have like x plus 1, and we have it 3 times that factor, and then we have x minus 2, and then we have that one with a 4 as the exponent. So the 0 that we found from here, that we will find, it will be x equals negative 1. So at that 0, because this number is odd, we will have the 0 will cross the x-axis because k is 3. So the multiplicity is odd. And then for the other one, since we have an exponent of 4 and 4, so that's k equals 4, which is even, then we will have the one that touches it and it turns around, or it bounces. Touch and turn, or bounces back from the x-axis, so it will not go through the x-axis. Okay, next one, intermediate value theorem. This gets overlooked a lot, but it's very important, and I will more than likely give you a question like this on your test because it's just so easy. So easy to grade. So what this theorem talks about, it compares two x values. So in this case, those two x values are a and b. So we're going to have x equals a and f of a okay. Okay, let's say f of a, I'm just going to give it a number. Let's call it, let's say it's a 2. Okay, then we have another one, which is b. So the x value is b. B is a number, so the y value that corresponds to b will be, let's see, let's call it a, let's say it's a 5. You can see that f of b is here, f of a is here. So if a is less than b and f of a is also less than f of b, this is also a good example of an increasing function, but what we want to say is that there is a number in between a and b for the x values, and here we're calling it c, for which f of c is also in between. F of c is right here. There we go. So that is an application of the intermediate value theorem. However, the most important application is, in this class, I guess, is the one to find if there's a 0 in between. So in this case, the y value for x equals c is here, and you see it's in between the y values for a and b. So that's why we can do these two inequalities. So if we apply this to finding a 0, it will go like this. A and b are real numbers, just like the other one, and we have that a is less than b. if f is a polynomial function such that we have to indicate first that f of a and f of b are not equal, because if they were equal, that we had the same y value, we will just have a constant function, a horizontal line. So we have to exclude that they cannot be equal, the y values that correspond to it. So then for that interval where a and b are located, there is a value in between them for which there's an x value. So let's break this down into x values again. X values. So we have x equals a and we have x equals b. So and on a number line, this 2 will be like this. A is here, b is here. Because we're saying that a is less than b, correct? So if we, and actually I want to do this drawing. I'm just going to move it. Oh, I don't know why it's not working. Oh. There we go. So let's just move this a little bit. Oh, and we're missing that. Okay, so we have that, and then I'm going to draw the y-axis here. So this is our x-axis, this is our y-axis, or our f of x axis. Okay, so we have those x values, and now for the y values, or the function values that correspond to those x values, we have f of a here and f of b here. So the trick here is to figure out if those have opposite signs. So for example, here we're saying that for x equals a, the polynomial function is positive, meaning this one here is positive. Let's place it here, f of a. So it will be a point right here. And then it says here that for x equals b, the function value is negative. So this function value is negative. So let's place it below the x-axis. So let's say is here. That's f of b. And so that would be like a point here. For x equals b, the y is negative. And then let me fix this one. It looks a little ugly. Let's just place it here so I can write. That's f of a. And we have it there. Positive because it's above the x-axis. The other one is negative because it's below the x-axis. So what is this intermediate value telling me now? Theorem tells me now that for the function graph to get from f of a to f of b, it had to cross the x-axis at some point. And I mean, I'm just doing dotted lines because we don't really know where exactly. And I don't want you to think that it has to be in the midpoint. It could be anywhere. It could cross it like closer to here or closer to the A. So I'm just going to do it like that. Okay. So that number right there, we're going to call that C for the x value. So for x equals c, then f of c is equal to 0. Meaning that if it is An x-intercept, it means that x equals c could be a solution or a zero or a root, and it's also an x-intercept. So that's all we get from the intermediate value theorem. It just guarantees that there will be a real zero represented as an x-intercept in between the interval a and b. So we could say a is here, c is here, and b is here. And this one right here is the one that contains the zero of the function, which is here. Okay, so how do we use it? You might have a question like this on your test. So it will say something like, use the intermediate value theorem to show that there is a zero between x equals 2 and x equals -1. So what do we have to do? Well, we have to find what is f of -2. And so from the original equation that we have here, everywhere where you see an x, we're going to substitute that with that number that we have here for our input. So I'm going to do that, -2 to the power 3, then -2 to the power 2, and notice how I'm putting them in parentheses. That's very important. And so if we, how do we say this? Simplify it. So -2 to the power 3 is going to be -8. -2 to the power 2 is going to be a +4, and then we have a +1. So that will be -8 plus 4 is -4 plus 1, -3. So what does it mean? That f of -2 is negative. Let's not forget that. Okay, now we need to find f of, it's right here, I can't see, of -1. So now I'm going to replace all my x's with a -1. So -1 to the power 3 from the original function here, plus -1 to the power 2 plus 1. So we will get -1 to the power 3 is -1, -1 to the power 2 is +1, and then we have another +1. So then this will turn into a 1. So what does this mean? That f of -1 is 1. So we do have enough evidence to say that f of -2 is negative, right? We got -3 for the output, and f of -1 is positive because we got +1. So what do we say as our answer? And we could see our points here to confirm. F of -2 is here. So as you can see graphically, there is a 0 in between those two x values. These were the x values that were given to us. We were given the x value of -1 to substitute right here. And then we got this point, right? And then they gave us x equals -2 right here. And we got this point. So because the y values this is positive and this is negative, they're opposite in sign, then there must be a point where the graph crosses the x-axis. Therefore, there is f must have a real zero because x is an x-intercept somewhere between, and I would like just to add here, somewhere in between x equals -2 and x equals -1. So there is an x value right here. We don't know what it is, for which we'll call it C, for which the y value is 0, making it be a 0, making it be an x-intercept, making it be a root, and also making it be a solution to the equation. Okay, so let's adjust this and move on. We're almost done with this section. Okay, so let's go ahead and do another problem. And this will be our last one. Yay! Okay, so we have different function is similar though. So we're going to be substituting here for x and here for x. Okay, so it says use the intermediate value theorem to approximate the real zero of that function, right? So we have two x values to work with. I guess I probably deleted them, for x -1 and x equals 0. So let's go ahead and start with those substitutions. So we have f of -1. It's going to give me -1 to the third power minus -1 to the second power plus 1. So this will be -1 minus, and then from here I get +1, but I had a minus here already, and then plus 1. So this is going to be -1. So that means it's negative. And then for the other one, which is 0, for the x value, we put 0 to the power third minus 0 to the power 2 plus 1, 0, 0. So the only value is 1, which is positive. So because we have that, 1 is negative. F of -1, we got -1. And then f of 0, we got +1. So it says here, because f of -1 is negative and f of 0 is positive, you can apply the intermediate value theorem and to conclude that the function has a real 0. We don't know what the real 0 is, and this is how you will answer this question on your test. You can apply the intermediate value theorem, or you can say something like, by the intermediate value theorem, there is a real 0 between -1 and 0. And I would just like to add between x equals -1 and x equals 0. I would like to add that. So where will that be? Well, as you can see here, we have the x equals -1. And here's the function value at that point. Here's the coordinates. And here is the value of x equals 0 right here. And here is our point on the graph and the coordinates. So you can see that for the graph to get from -1, -1 to 0, 1, it had to cross the x-axis. So that is what guarantees that there is a real 0 by the intermediate value theorem. There is a real 0 between the interval -1 and 0 for the x values. Okay, and that we don't know what it is. It's just, let's call it C for a constant. And that's it. This is the end of the video.